Hello everyone, and thanks for giving me this opportunity to speak today. In this talk, I would like to discuss how gravitational wave propagation over inhomogeneous spacetimes can produce lens-induced dispersion and how this phenomena may provide a new way to test dark energy and modify theories of gravity. Let me briefly outline the structure of this talk. I will begin by motivating the main reason behind this line of research, and then I will move on describing the general theory of gravitational radiation within the geometrical optics framework. I will then go through some technicalities, showing the method to compute beyond geometric optics correction, and finally I will apply the whole formalism to some specific cases of scalar tensor theories. I will draft the conclusion at the end and outline the main implication and future perspectives. Now, let us start this journey by assuming a propagating signal on the spacetime. Here, we usually have a very reliable and solid approximation inherited by the electromagnetic theory called geometric optics. This approximation is valid almost everywhere whenever the wavelength of the signal is much smaller than the size of the object that could be encountered during on its path propagation. However, gravitational waves, future detectors like LISA for example, could probe gravitational waves with a wavelength comparable to the size of some astrophysical objects. And that's why, in this case, we could have a breaking point for the geometric optics description and the necessity to go beyond and see what is going on. In this kind of scenario, we could unlock new features like new interaction and mixing between the propagating degrees of freedom, new insight on wave optics phenomena, and as a result, a new tool to test gravity. Now, let me begin by emphasizing that the story of gravitational wave in general can be mainly divided into three main stages: generation, propagation, and detection. In this talk, I will focus only on the propagation problem, namely what happens to the signal between the source and the observer. To study this, we linearize the equation of motion around a given background configuration. In the following, I will only use and focus on scalar tensor theories. That's why I will consider only the metric and a scalar field. However, the formalism I'm presenting now can be applied to multi-propagating fields, so it can be generalized accordingly. Now, if we deal with the cosmological background, for example, the large number of symmetries given by the Friedmann-Robertson-Walker spacetime strongly constrains the form of the propagation equation, making the gravitational wave evolution restricted to a very limited scenarios. However, we know that the real universe is not perfectly homogeneous. Gravitational waves travels through galaxies, clusters, compact objects, and in many modified theory scenarios, for example, possibly through screen scalar field configuration. This inhomogeneity then breaks the symmetries of the cosmological background and make the phenomenology of the problem, of the propagation problem, much richer. This is basically the starting point for us of this following discussion. Now, starting from the linearized equations, it is possible to write the propagation problem in a very general form, as we can see here in the slide. We collect all the propagating degrees of freedom into a single vector, which in our case contains only the tensor and scalar perturbations. The fluid dynamics then can be always separated into three different contributions, related to second, first, and zero-order derivatives. Here we have the kinetic matrix that defines the set of the propagating eigenstates, the amplitude matrix, and the mass matrix, which encodes dispersion phenomena. An important point on this feature is that mass-like term contribution always appear in every theory of gravity, making dispersive phenomena a universal prediction for theories beyond GR. And this will be a crucial point for our discussion. To solve this equation, we use the geometric optics expansion, also known as the shortwave expansion. We separate the oscillating phase with the amplitude and expand around a small parameter epsilon, which measures the ratio between the gravitational wave wavelength and the typical background scale. By plugging these ansatz in the linearized equations and collecting the contributions order by order in epsilon, we get the leading and next to leading order, as we can see here, that are describing geometric optics. Namely, we have epsilon to the minus 2, which gives information on the causal structures, and epsilon to the minus 1, that describes the evolution of the amplitude. Here we have the epsilon 0 term contribution that encodes the first correction to geometric optics. We can see that such corrections are sourced by the geometric optic amplitudes on the right-hand side of the last equation, and the aim of this talk is just to discuss a way to properly find a solution for the epsilon 0 contribution. Now, when the solution for beyond geometric optics contribution are computed, assuming to be computed, we can recast them in the geometric optic ansatz, thereby producing an additional frequency-dependent phase contribution. And this motivates the introduction of a lens-induced dispersion parameter here. This phenomenon for gravitational waves is closely analogous to what happens in optics when a light passes through a prisma. In our case, the prisma role is played by the gravitational lens. Now, in order to properly compute beyond geometric optics correction, we employ the null-tethered formalism, providing a suitable basis adapted to the propagation direction. The wave amplitude can be decomposed into different polarization components, as we can see here in the second equation of this slide. The short-wave expansion ansatz can be also plugged into the transverse condition, as we can see on the right-hand side of this slide. At the leading order, epsilon to the minus 1, we recover transversality between the wave vector and the metric amplitude, but at the next to leading order, epsilon 0, we can find that such condition is not holding anymore, and this feature has an immediate consequence for the polarization content, as we can see now. In fact, as we can see in this slide, transversality, when we are in the geometric optics regime, strongly constrain the form of the geometric optic amplitude, where the only surviving polarizations are those related to H plus and H cross, as we can see here. Everything is cancelled out from this condition above. Meanwhile, when we are in beyond geometric optics, transversality is lost, making new polarization mode, this one highlighted in yellow, to be unlocked. These are basically forbidden in the geometric optics limit, as we saw in the previous slide, and they are ready in a certain way to be excited at subleading orders. Now, geometric optics evolution equation in general can be solved explicitly, and the results and solution are already well known in the literature, so both for GR and scalar tensor models, for example. So for time constraint, I will not discuss them here, but let me focus instead on the anatomy of the formal beyond geometric optics solution we have in this slide. For example, here we have the G4 function controlling the non-minimal coupling between the scalar field and the Ricci scalar in the Lagrangian. Then we have the comoving distance d along the geodesics, parameterized by this affine parameter xi. And finally, we have the propagator operator we saw at the beginning of this presentation, encoding second, first, and zero order derivatives. Let me move now, to this purpose, to characterize the solution, the formal solution. And in this case, we need to specify the theory, specify the lens, and the geometrical propagation setting. So now we are going to describe two concrete examples we studied. The first one is the dispersion induced by a point lens in Brans-Dicke gravity, which was the first example studied in this line of research. The second one is the case of a spherical lens in synchrotron gravity. The propagation setup, which is the last ingredient we need, it's very simple. The wave propagates along the z-axis, crosses the lens region marked in orange with an impact parameter b, defined as b. In this case, we adopted a perturbative approach by expanding the amplitude in this way, at the bottom of the slide, where the final goal for us was to compute this highlighted um, correction that enters in the phase shift of the waveform directly. Now, this table summarizes all the results we obtained in our first analysis. The first important feature for us is the appearance of this apparent polarization, this NN mode, which is also present in GR, and it's a direct consequence of the loss of transversality between the propagation direction and the amplitude, of course, in beyond geometric optics regime. But most importantly for us is that we found corrections that directly affect the physical gravitational waves polarization, which are absent in GR, and these aspects mark a profound difference between the GR and the modified gravity. Let me move now to the symmetron case. Here the lens was modeled as a sphere with a constant density, while the scalar field exhibits the characteristic screened profile of the symmetron gravity. In these plots, in the following plot here, we used the Earth and the Moon as lenses for different allowed values of the symmetron parameter space. The quantity shown in this plot is the phase shift entering directly in the waveform as a function of the impact parameter normalized to the lens radius. We can see, for example, that unlike the point lens we discussed before, the spherical lens induce small dispersive effect also in GR. However, once the symmetron parameters are varied, the effect for the scalar tensor theories become significantly larger. In particular, the dispersion grows as the trajectory approaches the edge of the lens, as we can see here in these blue regions, and in particular reaches its maximum values close to the boundary. Meanwhile, we have an outside tail when we propagate outside the lens, which is not informative for us. We can finally translate all the obtained results into the symmetron parameter space. The interesting point is that here, propagation tests like this probe a new region for the symmetron parameter space, as we can see here in this plot. In particular, when dispersion becomes significantly large, one can identify a critical frequency, analogous in some sense with the plasma frequency for electrons, for example, above which gravitational waves may no longer propagate efficiently through the lens. And this is a very interesting feature for this kind of test. In other words, I want to claim that high dispersion may prevent gravitational wave propagation through astrophysical lenses, which could be an interesting feature for this kind of test of dark energy and modified theories of gravity. To conclude, I want to remark again that lens-induced dispersion phenomena are a universal prediction in theories beyond GR. This framework is nothing but a first step towards the full wave optics formalism, and of course there are many other things to do for this framework to build better models. I just mentioned 2 points here, which is extending the mathematical framework, extending the framework to non-fully luminar theories, which means to have, in a certain way, scalar waves and tensor waves propagating at different speeds, which means to have a richer structure, two different causal structure and a richer structure in order to get more phenomenology from this framework. And of course, we want to test and add different lenses, different scalar field profile, as well as new theories to be investigated. Thanks for your attention.